need to be. Okay. Let's do this here. Where'd it go? Well, pick up the one with the problem. There it is. Oh, yeah. So here's one that just a dy. Just a line integral with dealing with y.
Is that x squared y?
X squared y, yeah. Thank you. The letter y is mean to me.
Is there a parenthesis before the y?
Is that cool?
Plus sign? The sign.
They're there?
Yeah.
Yeah. Is that black marker you're using? Yes. All right. Oh. So now we're going to use the more specific definition of this. And in fact, so this is not the one where I need the full-blown square root of all that business there, right? I just need the y prime of t, since this is dy. So first off, how do I want to use my t? How do I want to introduce my parameter into this? And notice this is a little segment, but this is so nice if you are nice to yourself. They both start at 0, which makes things so much easier. So if I let x be what, then y has to be what? Don't overthink it.
Oh,
Don't bring trig in. Let me just help you right out.
Pi squared.
If x is t,
T squared.
then y is t squared. So the most basic way to parametricize anything is to let something be t. So I could have chosen y to be t, and then x would have been root t. I'm not going to do that to myself necessarily, right? I kind of want to stay away from radicals if I can. Maybe it won't make it that much worse, but why do that to yourself? Okay. So what's t go from to? And why is that really, really easy here? Because x is t.
0 to pi.
It goes from 0 to pi. I like it. Sweet. Okay, so t goes from 0 to pi. Or how did I see that?
Yeah.
X and y have to start at 0.
Right.
So because of the way I define them, t has to start at 0.
Okay.
I like it. And then x has to get up to pi, and y's got to get up to pi squared. So it's got to get up to the value of pi for x.
Oh.
And that does give me a pi squared for y. Cool. Is it always going to be that easy? No. One of the points was the origin, so that's nice. Right. But if it's not the origin, then you just adjust. If I don't, I can certainly make one up as an example.
So then,
Oh yeah, we can try that one. Ooh, that one's kind of gross. All right, so now I just got to figure out, yeah, what that's going to be. Let me see. Did they ask this way?
would be
Oh, cool. All right, I like it. So let's see what happens. We know it goes from 0 to pi. We know what x and y are. So this will be t squared times t squared plus sine of t. Now this is going to be, and let's see why this makes sense. Yeah, exactly. So y is t squared. So what's dy going to be? 2t dt. I like it. And this part, of course, is just that y prime of t that they're talking about in that definition from earlier. So that's why that's not that big of a deal. It's that part that's just going to be sitting there. It's just the derivative of y. Of course it is. I got to take the derivative to figure out what dy is. So I've got this whole thing times 2t dt. So the more you understand parametric ideas and how to parametricize some given thing, the easier this process is going to be. Because then once you do that, it's all just plug and chug. And then you're back to nice, normal Math 180 integrals, to be honest, if you notice so far at least. All right, so you bring that in. So let's see, it'll be 2. It'll be t to the 5th. So you integrate that, and you get.
T to the 6th of the 6th.
And it'll be t sine t. Oh shit! Let's take a minute for that. Yeah, see that? Let me slow this down a little bit. All right, Jeff. So you get t to the 5th plus t sine t. I got a 2 out there. This guy I'm going to have to use what? By parts. I like it. That's why I chose this. So this part's easy. This part needs a little help, but it's not that evil. Obviously, what do you let u be here for your by parts? T, because one derivative and it's gone. So if u is t and dv is sine t dt, then du is dt, and v is going to be negative cosine. I like it. Cool. So then this will be twice t to the 6th over 6. Yeah, exactly. uv minus the integral of v du. The integral of v du would be negative cosine t dt. All right, make sure you guys. I mean, I'm doing this a little bit loose because this should be something you can sink your teeth into. You should know how to do this kind of stuff relatively easily. I need that here. I don't want to write the whole damn thing over again. Let me just figure this part out by itself over here. Integral cosine is sine minus a negative is plus, and I want to evaluate from 0 to pi. Crazy shit, and then you just plug that stuff in there and see what happens. All right, we've got another weird pi to the 6 kind of thing.
Why is it not minus sine?
Oh, so it'll be uv minus the integral of v du. I like it. So when you do this, you don't have to be as loose as me. You can be a little more. And please, you guys, just plug stuff in and see what it is, right? All right, I like it. Cool. So here's an example of one that wasn't a circle, but you still just try the simple parametric stuff first. Let's see. Do I want to do one more? Yeah, let me do one more, and then we'll do a little bit out of 16.3, and then we'll call it a day. It's a pretty packed day. I like it. Well, let's see. I'll give you a choice for the next one that we're going to do. Do you want to do one that's a DS one again? Or do you want to do one that's... where'd it go, Jeff?
Yes.
That involves endpoints that aren't 0, 0? Or that actually involves... You might want to do this one. The parametric... I'm sorry, the piecewise defined curves. Oh, that sounds awesome. Oh, that sounds awesome. Who cares, guys? It's just 2 integrals instead of 1. Oh.
Exactly.
All right. There you go. Somebody understands? So look at this.
No, that's why it's little.
Oh, I see. Oh, well, somebody completely doesn't understand. Okay. Now notice the notation here. This gets kind of interesting. I like this. A single integral, but dx dy. So that's just, yes?
Is that lambda? Or 7?
No. What do you think is lambda? This?
No.
It's just a 7.
Oh, that's a 7. Oh.
That's a number 7, yeah.
Okay.
It's number 7 from the book. And it's defined over C's line segments from 0, 0 to 2, 1. And from, where'd you go? From, there you are. 2, 1 to 3, 0. Yes.
So then we subtract final mass initial, and then you have 2 coordinate points to work with.
Oh, there's several different ways to do this. Let me give you guys a couple. Try to figure out. There's 2 separate curves here, right? Because there's a little kink in the middle here. They don't have the same slope between them. These are just line segments. Figure out the parametrization for both.
These are just lines.
That's a word that makes you sound drunk.
Straight lines?
It's just straight lines.
Oh.
Just the line segments. Exactly. You can get very different ways to do this. If you want to. That would help you out. All right. You don't have to use that. You could if you want to. That's a line segment between 2 points, where like this would be vector 2, 1, the vector pointing to that point. So that would be like R0 and R1. This should be easy though. All right, so let me see. I think somebody is probably more willing to tell me this one. This one, hopefully.
2T.
Yeah. So if you call YT, then X could be 2T. I like that. 2T. And that's letting T go from
0 to 1.
0 to 1. Now you could say that's T and that's 2T. Or you could say this is T and that's 1/2 T, is what I'm trying to say. And it goes from 0 to 2. Right? I mean, there's a lot of different ways to do this. So when you calculate that square root of the dx dt, dy dt, some of you guys might realize the way you define this changes how quickly you traverse that. And that's what I was trying to say. That's like a pacing adjustment, velocity adjustment. I don't know how else to say that. Or it's just a thing you got to do to make it work. That's another way to look at it. What about, anybody got a suggestion for that one?
Could you do x is t and y is negative t? But if you're like making that a vector, kind of, it's 1, negative 1. Can you do that or not?
Oh, so okay. Now you've identified the direction vector from 2, 1 to 3, 0. What you didn't take into account is your initial point.
So it would be T plus 2 and negative T plus 1.
So if you wanted your t to go from 0 to 1, so you can kind of start there or not. So you identified that from 2, 1 to 3, 0. You have to go over 1 and down 1, right? So this is what this is like the V. You guys remember that from defining a line? That's your slope vector in a way. It's your direction vector. But you have to add to it your initial position, right? Why did I put a negative there? So then what do you get if you do this? You'll get,
2 plus t.
and this is times t, right?
Yeah.
I like it. So you get 2 plus t,
And 1 minus
1 minus t, exactly, which is pretty much what you said, right? So that's, if you just think about it, if you say this is 2, starts off at 2, so when t is 0, it's 2. And to get to 3, I can add t and let t go up to 1. So that kind of identified what t is going to go between. So you can do it this way. There's nothing wrong with that, which is actually basically that, to be honest. Or you could do it this way, which is just kind of figuring out if t is 0, I get 2, and if I let t go to 1, I get 3. It's amazing. Now at 0, I want it to be 1, and at 1, I want it to be 0. There you go. So you do have very controlled kind of ways to do it, or you have kind of less controlled and more just free-flowing. What makes this work? There are different answers for this, but depending on how you define t, but that's the most basic way to do it. I like it. Now, real quick, why does it make sense that if I change, instead of going a line segment and another line segment, if I just went there on a curve, will my answer be the same? Remember the
length will be different?
Yeah, the length of the arc.
What's more important? Well, yeah, you start at the same place and you end at the same place, and the length of arc will be different, but so will my pacing will be different too. So maybe those. But what's the more direct way to answer that question? Because it's all about really what's the end result of this interval really related to. It's all about what the hell the outputs are doing. Right. So if I'm going from one point to another point like this, and I say, well, what about if I go like that? Well, I don't know what the output's doing. Maybe the output's negative over here and positive over there.
Path independence?
That we're slowly getting there. When we talk about, right now we're talking about line integrals just by themselves. When we start doing line integrals across vector fields, if it's conservative, then it doesn't matter what path you take. Which kind of makes more sense about the word conservative. It conserves, it doesn't have any excess stuff that it loses. It kind of, whatever it loses, it gains back at the end. That's one reason why we call it conservative, yeah.
Can you do the way with the day for on the line segment?
Yeah, sure. Oh, can I do it?
Yeah.
So it would be, this would be 2, 1 times 1 minus t plus t times 3, 0. So it'll be, what do you get here? You get 2 minus 2t, 1 minus t, plus 3t, 0. So you get 2 plus t and 1 minus t. All right, so mathematically it's the same damn thing. Here you explicitly calculated the difference. Here you calculated the difference within the problem. Anyway, okay, one way or the other. All right, so now we can start actually doing the problem. Holy shit. Do you guys understand now that I need two intervals, right? So, and they're both 0 to 1 for t, but I have different definitions for x and y on both. So I have to use two different intervals. So one would be 0 to 1. So I'm going to use this, I'm going to call this curve 1. And of course you guys are all past the point where I can call a straight line a curve. I love that. Like the straight angle is a straight line. It's, yay, math. Okay. 0 to 1, x plus 2y, so it's going to be 2t plus 2t, 4t. And what's dx going to be? All right, let me slow down a little bit, sorry. Is everybody cool with what I'm doing right now? I've got everything defined. Now I just got to throw it in. So over curve 1, x is 2t and y is t. So it'll be 2t plus 2t is 4t. What's dx? 2 dt. 2 dt. Plus,
4t squared.
good, 4t squared. What's dy? dt. And then I got to do one for curve 2, right? Plus, curve 2 is going to be there, and it's still 0 to 1. X is 2 plus t. Y is 1 minus t. Get in there. What's dx for curve 2? dt. Is everybody with me now? I'm just doing the same thing just for curve 2 now. Where'd it go? dt. Plus x squared. 2 plus t squared. dy is going to be
Negative.
negative dt. I like it. So it's kind of nice. We decided to just write that one integral for multiple things. It kind of makes it quicker. You could just kind of put this all together now if you wanted to. But so what do we get here? We get 8t. Now it's math 180. Is that cool? I mean, again, the hard part is getting here through this. And once you're here, it's just, now you're back in math 180. I mean, enjoy that. So I'm not going to finish that. Thank God. All right. That's nowhere near the interesting stuff. Like, we don't want the interesting stuff.
So it doesn't matter that there's like 3 GTs in one integral?
The notation, you can kind of just put these back together now if you want to, but it's up here, it's we want it clear because if I'm doing dx, then I need this pacing. If I'm doing dy, then I need this pacing, right? And that's why this was just dt and this was 2 dt. Right? After that, it doesn't. Then you can just put them back together into one. I don't know if they give you a full example like that.
So then it would just be from 0 to 1, 8t plus 4t squared dt.
Yes. Cool. Oh, here we go. Yeah. Example 6. They show you just slam this stuff back together. I like it. Oh, we're there. All right. All right, I think the last bit here. Oh, yeah. All right. The nice thing with section 16.3 is it should be relatively quick. We got one little piece in 16.2 left to do. That was the next section that did this, but it's this section that does this. I like it. Bless you. Oh, let me see. Oh, that's right. I didn't want to do too much of that. So let me show you this picture to give us, before I finish writing that out, I'll show you this picture here. You do whatever you need to, Joe. Aw, thanks, guys. This is what I was talking about earlier with going across vector fields, doing a line integral through a vector field. So to be more general, this could be some three-dimensional vector field, and then R of t would be some three-dimensional space curve, right? Space curve. Less successful follow to space curves. So here we have this. Now they're trying to make it this same kind of looking thing we had earlier, but now it's definitely in 3 space. I'm going to try to bypass some of this summation notation business in the leading up to the actual integration, and just hopefully the idea makes sense. If I have some vector field F, and at this point, it's pointing that direction, then the only part of that that's acting along my path is going to be the tangential part of it, right? Does that make sense? Yeah, so what I really want then is the dot product between the F and that tangential vector at my curve. So now look what happens to the function.
You're saying that dot product will give you that tangential.
Right? There you go. So then I've got, if I want an integral along some curve of some vector field, it's going to be dotted with my dr, my little r element. Now this is where, this is not a huge step to take, hopefully. If r prime of t, where do I want to write this down? Oh yeah. I mean, this is just silly. If I have r of t, what's dr dt? R prime of t is amazing. So then what's dr? Okay, that's amazing. So dr is r prime of t dt. And then I have my f at r of t. So r of t, what are the components of r of t? X of t, y of t, z of t. So what we were doing earlier, like somebody pointed out, you could use just r notation to capture all three of those components, but it's just a difference in notation, really. Here, to make this more general, we're going to go in and use that notation. And then what's this big-ass t thing here?
The tangent vector.
The unit vector, tangent unit vector. I love it. Right? And we talked about earlier, you can look them back up if you want to, the relationships between ds and the tangent vector and all that stuff. But if you use what we know, we get there.
Do you have to make it a unit tangent vector? Or not?
Yes.
Yes, because it's all about the outputs of f. I don't want the length of this thing I've chosen to actually influence that at all. I don't know if they actually address any of that. Blah, 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 blah. Okay, let's see. Don't want to do something with that. Oh, we could do some examples probably, but let me see. Okay.
Wait,
Yes.
hold it.
So this is, of course, I need you to understand there is a whole little section about working our way up to that formula step by step. The idea behind it is just so simple, so beautifully simple that I just wanted to get right to it. We do have a given vector field, so that's different from what we were doing before. Before it was a line integral over some curve with some outputs. Here it's a vector field that I'm doing a line integral through. Yes?
So this is something like accumulating force over a path.
Yeah,
And
or
that's why the dot comes in, because the direction of the force, you're not always going to get the total force in your direction.
exactly. So how do I want to say this? So it's like a work only is a dot product because I only talk about the motion that's in the direction of the force. So it's the same kind of idea more generally for any force field or field function that I'm talking about. Yeah.
Summation of the vectors.
Yeah, exactly. I like it. So there's a lot of different little ways to think about it. Let's see. I don't really have an example picked out, but we can just do one of these. So if I have this, so this is a force field. We want to move a particle through it along, so move a particle along this path. Bless you. So, oh yeah, I lost it. Let me put this up here and keep it for us. So now I got to figure out what f of r of t is. It's not too bad. F is this, so what's f of r of t? It's just going to be f of x of t, y of t. Which is going to be what happens here. What's the x piece going to be?
Cosine squared.
Yeah, so cosine t is x, so I get cosine squared. Let me just write like this. Negative, what's going to happen here?
Cosine sine.
Cosine sine.